So previously we looked at the ways of how we can find the roots, or how we can locate the interval within which the root of the equation is expected to lie, and also we saw how we can locate the actual root. Say that the change of sign method cannot locate the interval where the root of the equation is expected to lie, but the graphical method can be used to locate the interval where the root is expected to lie, and also to locate the actual root we can use the graphs. So now here, when you look at apart from the graphical method, there are other methods which can be used to sort of find the root of the equation. One of the methods we know, because when you're using the graph, you can locate the actual root of the equation. Now we can also use the linear interpolation to find the root of equation of any degree of any family. Now this one here is a product of a linear function and exponential function. We shall also look at the sine, the tan. These ones are trigonometric functions. We shall also look at how you can find the roots of these other equations. One of the methods that we are going to discuss is using the linear interpolation to obtain the roots of the equation. Now when we look at this question here, the equation is show that the equation f of x is equal to 3xe minus 1 is equal to 0 has a real root between x is equal to 0.2 and x is equal to 0.3. There are two ways of how you can show how to show that the equation has a real root within that interval. And we say that one of them it is in the graphical method. You can either use a single graph or you can use a double graph to confirm that actually the equation has a real root within this interval x is equal to 1 and x is equal to 2. Then the other method is the change of sign method. Now in a question like this one, where they have not specified that use a graph, don't use the graph because the graph is time consuming. So in a situation like this one, we can easily show that the equation, the root of the equation lies in the interval 0.2, 0.3 by using the change of sign method. If it used to use the graphical method, it will consume a lot of time. So we come and find that now our f of x is there. Let us use this bigger space here. Our f of x is equal to 3xex minus 1. So what we do, we substitute in these boundaries, the lower boundary and the upper boundary. So we substitute the f of 0.2. Then this one will be 3 times 0.2 times e power 0.2 minus 1. Then we substitute in this one, f of 0.3 is equal to 3 times 0.3 times e power 0.3 minus 1. So if we see a change of sign in the function, then we make a conclusion that there is a change of, there is a real root within this interval. We're going to see how we make a conclusion. So in this case here, if the graph, we're going to use the graph when you have been required to use the graph. Because the graphic is time consuming. But the situation like this one, show that the equation has a root within this interval. Use the change of sign method by substituting in the lower boundary and the upper boundary. If you see that there is a change of sign, then you know there is a root of the equation. So if we use the calculators here, you will find that the value here is 0.2672, and this is negative. Then this one here is 0.2149. So since you clearly see that when you substitute in the 0.2, we get a negative value. When you substitute in here, you get a negative value, you get a positive value. So you conclude that since the f of 0.2 times the f of 0.3 is equal to, we multiply those two, you can use the calculator there. The calculator here, find that you are having the answer, which is negative 0.0574. So since the product of this one and it is less than 0, then there is a real root between x is equal to 0.2 and x equals to 3. So you conclude that since when you multiply is 2, you get a value which is a negative, and a negative is less than 0, then you will make a conclusion that there is a real root of the equation within that interval. So the next step, they want us to use to obtain the root of the equation to one decimal place. They have given us the condition that the root should be given to one decimal place. So if you have to give the root to one decimal place, we are going to be following this condition of one decimal place. If it is two decimal places, we follow the condition of decimal places. Now, using the linear interpolation. So if we are doing that, if you are finding the root of the equation for the error between the beta approximation minus the previous approximation, it must be less than 0.5 times 10 power negative n, where n is the number of decimal places. Number of decimal places. Now, like this one here, they have given us that we should give the root to one decimal place. So, which means that we are going to look for the first value of the root, we'll look for the second value of the root, then we subtract those two. If we find out that the difference between the first and the second values, when we're using the linear interpolation, the first and the second values, when they're giving us a value which is less than 0, for example, the first and the second, because we're going to first get the x naught, the initial approximation, then we get the second approximation, we subtract them. If we find that we are getting the root to one decimal place, so we should be 0.5 times 10 power negative 1. If it was to two decimal places, because the condition has been specified here, and we should give the root to one decimal place. So which means that the condition we are following, that when we subtract the two values which are obtained, we must get a value which is less than 0.5 times 10 power negative 1. And this one here is it. It will be now x1 minus x0 should be less than 0.05. And if this condition is fulfilled, you cannot stop. You continue performing iterations until the condition of the decimal places has been fulfilled. Unless they have given another condition, because they can tell you use linear interpolation once. So which means that one, the condition of decimal places stops to work. But if they have not mentioned the number of times you should use the linear interpolation, means that you are following the condition of the number of decimal places. And this is what we mean here. This is what I mean. So we are going to come back to these values. We are coming back to these values and we draw our table. A table of x with the corresponding values of f of x. So the first value of the x is 0.2. So we write the 0.2 here. Its corresponding f of x is this one, which is negative 0.276, negative 0.2672. That is when you substitute in the 0.3, the function, we are getting this. Then here, if this one, if x naught is the root of the equation, because we are looking for that root. If you have a value x naught as the root of the equation, then when you substitute it in the function, you must get 0. If x naught is the root of the equation, when you substitute the x naught in this function here, we must get 0. But we don't know the x naught. So that's what we are looking for. So now we come and get the upper limit with the upper value, which is the 0.3, and this is 0.3. When we substitute it in here, it gave us 0.2149. Those are the values that we obtained. So you first come and say the values which are given in the boundaries. In most cases here, they will give you the intervals. When you have to use the linear interpolation, will give you the interval. But if they are not giving you the interval, where the root lies, you have already known how to establish the interval using the change of sign method. You draw your table and you see where there is a change of sign, then you establish. But in most of the cases, they will give you the interval. So you get to substitute the lower limit, the 0.2, you get the value. 0.3, you get the value. Then you say now, if x naught is the root of the equation, when you substitute it in this equation, then you must get 0. That is the step. So what we do, we use the linear interpolation change of sign method. I mean the method of the gradient. We are getting the change in y. We are getting this one, which is 0.2149 minus. We are subtracting this, so it becomes a plus 0.2672. Then everything is over changing x, which is 0.3 minus 0.2 must be equal to change in y will be 0.2149 minus 0 over change in x, which is 0.3 minus x naught. So when we use the calculator, here, you know how to do it. When you use the calculator and you compute the whole of this one here was giving us a value which is 4.821. Maximize the number of decimal places, and this one is equal to 0.2149. Everything is over 0.3 minus x naught. So when we cross multiply and we bring this one this side, we have when we take this one this side, this one we have 0.3 minus x naught, and this one is equal to 0.2149, and everything is over 4.82, 4.821. Then here this one will give us 0.3 x naught equals, when we computed the whole of this result was giving us 0.00542. So when we make x naught the subject, by taking this one the other side, the x naught was giving us x naught was giving us a value which is 0.25542. You maximize the number of decimal places for calculation purposes, and you can clearly see that the x naught will pluralize between 0.2 and 0.3. First way you have to calculate, and you said the x naught lies in this interval, then you get a value like 0.19. That one will be incorrect because 0.19 does not lie in that interval. So you can say 0.25 implies in that interval. So what we do, we perform the next iteration. Because we want to check on this condition of the xa plus 1 minus xa. Is it less than that 0.5 times 10 power negative n? Until that condition is fulfilled, you don't stop. So now after getting the fx naught, the x naught, you come back to this equation. And substituting the f of x naught with our f of x naught is 0.25542, which is the same as we're substituting there. 3 times 0.25542, then e 0.25542, then minus 1. And if we do all the math here, when you use your calculators, I've already quoted the result here. When you use the calculator, you get a value which is negative 0.01808. That's what you obtain when you substitute this x naught in the equation. So what you do the same thing. And you say that you start with the values of x, f of x. We draw our table, and here we are having the values of x. And the value of x, we are starting with x naught, which is 0.25542, and this corresponding value is negative 0.01808. So now if x, the f of x naught, we substitute it here, this is what we obtained. Then we get now the x1, because we need to check on this condition here. We need to say the next value minus the previous value. When you substitute those two values, do you satisfy the condition of the number of decimal places? So now we have got the x naught, then we are getting the x1. So this is the x naught, this is the corresponding value of, this is our x naught, this is its corresponding value, f of x, then we get the x1. And if x1 is the root of the equation, then when you substitute it in the equation, you must get 0. You must get 0. Then we write these other ones remains, the 0.3, and was corresponds 0.2149. Then we do the same thing using the method of the gradient, changing y, so it is 0.2149. This is a negative, it was supposed to be minus, but this is a negative, becomes a plus 0.0180 over changing x, substituting this one minus that, 0.3 minus 0.25542. And everything equals changing y, this one minus this, 0.2149 minus 0 over this one minus this, which is 0.3 minus x1. So when we use the calculator and get the details of all that, it was 3.12389. This one equals when we subtract, we make with the 0.2149 over 0.3 minus x1. When we cross multiply, this side we shall have 0.3 minus x1. Everything equals 0.2149 over 3.12389. So the 0.3 minus x1 here, when you use the calculator, it comes up to 0.00579. That's what we get. So when we make now x not the subject, I mean the x1, will give us when we take this one inside, then this one. So it comes to now x1 will give us 0.2. So what was it? 0.26121. So you check on the condition, and the condition is the x1 minus x naught. Subtract those two values. What is it giving us? Because you said that for one decimal place, the difference here should be less than 0.005, because it is the condition is xn plus 1 magnitude minus xn. This one is supposed to be xn, not x1. Let us change to xn. xn plus 1 minus xn. So the xn plus 1 minus the xn should be less than 0.5 times 10 to the power negative 1 for decimal place. So this is 0.01. So when you subtract those two values, the 0.26 minus 21 minus the our x1, which is 0.25542, and the answer here was 0.006, and this one here is less than 0.0005. The value which you get after subtracting the two values, there are two zeros here, 0.06 is less than 0.05. So which means that the condition has been fulfilled. There you stop, and you set out the root. Easy, then you come back to this step. They said you want to choose one decimal place is 0.3, because you are rounding it to one decimal place. You said the root has been given to one decimal place. If the condition was not satisfied at that point, we will perform another iteration and we get the x2. If x2 was not giving us, then we got x3. We can use another example to see what how we can find the roots of the equation using the linear interpolation. Now here I said show that the roots of the equation tan x is equal to 4x squared minus 1 lies between x is equal to 1, 1.4 and x is equal to 1.5. Hence, use linear interpolation to find the root to two decimal places. So for two decimal places, it means that the difference between xn plus 1 minus xn should be less than 0.5 times 10 to a negative two decimal places. So which means that the condition we are following is xn plus 1 minus xn should be less than 0.005. That is the condition that we must satisfy before we stop performing the iterations. So we start by getting the fact showing that the equation lies within the party. The equation, it is tan x, but remember the equation which we want, it is in the form f of x equals to 0. So what we do, we bring this one this side, we make this one cross the equal sign such that we can express it in the form f of x is equal to, also we are solving the roots of the equation in the form f of x is equal to 0. F of x is equal to 0. F of x is equal to 0. So what we do, we bring this one this side, bring that one that side, such that it becomes tan x minus 4x squared. This one becomes plus 1, everything is equal to 0. So that is the form that we are. Then we first they want us to show that the root lies within that interval. We are going to use the change of signing method to confirm that the root lies within that interval. So we have our f of x equals to tan of x minus 4x squared plus 1. So we substitute in the f of 1.4. This will be tan 1.4 minus 4 times 1.4 plus 1. Then 1.5 tan 1.5 minus 4 times 1.5 plus 1. Make sure that the calculator is set to radians. The calculator must be set to radians at this point here. You get our f of x, substituting the values of x is equal to 1.4, 1.5. Then you substitute in. When you use the calculators there, this one was negative 1.0421. This one was 6.10142. And since there is a set of signs, this one negative is positive, then you confirm that since the f of 1.4 times f of 1.5 equals to, let us multiply those two here. The answer is 6.3 negative 6.3583. This is the negative value, it is less than 0. Then the root lies between x is equal to 1.4 and x is equal to 1.5. You must use radians. If you don't use radians, you will get different answers. You might get when both values are positive or negative. Then you say that there is no root within that interval because there is no change of sign. But when you use radians, you get the actual answer. So we come to the part of using linear interpolation. We do the same thing that we did earlier. We use the linear interpolation here. We draw the table. We have values of x, we have values of f of x. So we have 1.4 corresponds to negative 1.0421. This one here. Then if x naught is the root of the equation, then when you substitute there, you get 0. When you substitute the upper boundary, is 6.10142, and it's next door. This one here, it is we're substituting the value of 1.5. So substitute 1.5, then this corresponding value is 6.10142. Those are the corresponding values of f of x. So we use the same method of the bracket, changing y, changing x. So when we do that, we shall have 6.10142 minus, this is a minus, becomes a plus 1.0421, and everything is over, changing 1.5 minus 1.4, and everything equals change in y. This is 6.10142 minus 0 over 1.5 minus x naught. So when we compute the whole of that one, we shall have 1.5 minus x naught because we are cross multiplying the whole of this one here goes down here. Then this one here will be 6.10142 divided by the whole of that one. And when you compute that one, the answer is 71. The whole of this one here, it is 71.4352, and the whole of that one, when you divide, it becomes 0.0854. Then the x naught, when the x naught is moved the other side, then this one will bring to be 1.4146, and that is the value of x naught. So the computation here, you must compute the way how you have your algebra, and then the way how you want. First get this term here, then you cross multiply, you divide it, and then you make 1.x naught. Then you make x naught and something else. After getting the x naught, we come and now get the f of x naught here, and the f of x naught we are substituting tan of the x naught, which is 1.4146. 14, then minus 4, minus 4 times 1.4146 squared, then plus 1. We are substituting in this equation here. This is our original equation. We are substituting the x naught in that equation to get the f of x naught. And when we use the calculators, that value was when you use the value is negative 0.6543. That is the value we should come up with. Then you use the same table, values of x, values of f of x. So we start by writing the f naught here, and our f naught is 1.4146. Its corresponding f of x is negative 0.6543. And then if x1 is the root of the equation, when you substitute in the equation, you must get 0. Then you write the upper boundary, which is 1.5, 6.1042. Then we use the same method of the gradient, changing y, so it's 6.1042 there. Then this is the b plus 0.6543 over changing x, which is 1.5 minus 1.4146 equals to the change in y is minus the b6.10142 minus 0. Then change in x, which is 1.5 minus x1. So when you do all the math, you make x the subject, you come up with x1, which is 1.42287. When you calculate all these values, then you make x the subject, you come up with x equals 1.4227. Then you come to check on the condition. Our condition is here. The condition, they said that we should give the answer to 2 decimal places. And for 2 decimal places, the difference between those values should be 0.002. So we are going to subtract the x naught and x1, and we see whether the condition has been fulfilled. So we say now the x1 minus x naught is equal to, substituting the values, x1 is 1.42287 minus 1.4. The x naught was is 1.4146, and when we get the difference there, the difference is giving us 0.0083, and this one here it is still greater than 0.005. This is greater than 0.05. So which means that we must perform another iteration. After checking, getting the x1, and this one was the x naught, when we subtract these two values, we realize that we are getting 0.08, yet our error, the difference is 0.05. So this 0.08 is bigger than 0.05, means that we have not yet satisfied the condition of the 2 decimal places. We perform another iteration. And how do we do it? We we get the x1, this value of the x1, we substitute it in our equation, which is that x minus 4, x squared plus 1. We substitute in this value of x1. Then when we substitute in the value of x1, when we substitute in the value of x1 here, we substitute the value of x1, make sure that the calculator is the radians, then it's tan here, the value which you come up with negative 0.379. So there we come now and write this is the x1 and this corresponding value of f of x. Then we say if x2 is the root of the equation, then 0, when you substitute in this equation, you must get 0. We're looking for x2. Then this one here stays 1.5 and this corresponding value is it remains the same. Then we use the change of the bracket change in y, subtract this one is. This is the negative, becomes a plus here, then over changing x, then you do the same thing, change in y, this value minus 0, then change in x 1.5 minus this one here was supposed to be 1.5 minus x2, because change here, we are subtracting this one minus 0, so it should follow 1.5 minus x2. So when we do the math and we make x a subject, we come up with the value x2 is equal to 1.42278. Then after getting the x2, after getting the value of the x2, check on the condition x2 minus x1. The first one, the other one was x1 minus x0. Now this is x2 minus x1. When you subtract these two values, the meaning of this magnitude, you have to keep on putting them there. Even if you get a value which is negative 0.00426, even if this value was a negative, you present it as a positive value. You don't use you put the magnitude to eliminate that and that negative. So even if you get a negative value inside here, you present it as a positive. That is the meaning of those absolute signs. So when you subtract, you get 0.04, and 0.04 is less than 0.05. So which means the condition of the two decimal places have been fulfilled. Then you come and say now our root, because it was here 1.427, so we round it off because they want it to two decimal places. Then you come and say now this will be 1.43, because this is 1.427. You round it off, you get 1.43 to 2 decimal places. And that's how we use the linear interpolation to find the roots of the equation.